So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now just in Einstein's general theory of relativity, actually it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not, and is still not, understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are, we have a problem with the singularity, we don't really have any access to it, we don't have the conceptual tools to explore it, so it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole. Not in this extreme place, not only in this extreme place, singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important. The modern revolution in our thought, which is still ongoing, by the way, in understanding black holes and quantum gravity, really does begin with work that Stephen Hawking did in the mid-1970s. Stephen Hawking, in his own words, showed that black holes ain't so black. So we've described them as prisms, in a sense. We're picturing them as a region of space from which nothing can escape. What Stephen Hawking showed in a landmark couple of papers, a tour de force of calculation actually, is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow, they produce particles, they have a temperature. This thing that we pictured in Einstein's theories as pure geometry, as just distorted space and time, actually emits particles. It's called Hawking radiation. And one way to picture that, and Stephen in his 1974 paper gives this, he says it's a hand-wavy description. So it's not a full description, you need the mathematics for that, but he gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to imagine, to zoom in on space in the vicinity of the event horizon of a black hole. If you zoom in on any piece of space, the piece of space in front of your nose right now, if you could zoom in and slow time down with a big microscope, you can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. So it's a picture of what the vacuum of space looks like. Just to emphasize again, it's not a complete picture, it's not supposed to be precise, but it's a reasonable model of what's happening. So particles in and out of existence all the time. And that's happening everywhere, in space, everywhere that you look, in the most empty piece of space you could imagine. That's what's happening. In the vicinity of the horizon of a black hole, you can have the situation where one of those particles, those pairs of particles, is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe. It's essentially made real by the presence of the black hole. So the other partner is interior to the black hole, and this particle heads off into the universe, removing energy from the black hole as it goes. This rain of particles, this glow of particles, is called Hawking radiation. That has profound implications. So it's kind of a simple picture of what's happening. But the upshot is, imagine this thing. It's a black hole. It's glowing. It's just space-time geometry. But it's emitting particles, losing energy, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons. They have a lifetime. One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, a region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation, those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true, or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Let's say that I take anything in here, in this room, a book, a table, the camera, right, anything at all, and I set fire to it, I incinerate it, I destroy it in any way that I can. I could throw it into a furnace, I could put it in the heart of a nuclear bomb and explode it, whatever, just completely incinerate it. In physics, in basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, and I was clever enough, then I could reconstruct the thing that I had destroyed. Information is conserved in the universe as far as we know. So every law of nature that we have says that information is conserved. The problem was that Stephen Hawking's initial calculation of the way those black holes evaporate away said that information is not conserved. It said that black holes are erasers of information. To put it very bluntly, the calculation said that once that black hole had gone, then even in principle, there is absolutely no way you could learn anything, reconstruct anything about the things that fell in, including the star that collapsed to form it. So information erasers the only information erasers that we know of in nature. That was the initial picture of black holes as Stephen Hawking understood them back in the 1970s and 1980s. This became known as the black hole information paradox. So we have a situation in the 1980s, 1990s, 2000s, where it appears that there's a fundamental problem with our understanding of something. Black holes, quantum mechanics, general relativity. When you put them together, you have this apparent prediction that these things erase information from the universe. Some physicists, Stephen Hawking initially actually, felt that that was the case. That maybe these things do erase information. Maybe we don't care about that. Maybe that's the way the quantum theory of gravity is. And other physicists, people like Leonard Susskind initially, for example, George Hooft, the great Nobel Prize winning particle physicist, and others, felt that no, there's something wrong with our understanding. There's no way in which we can allow these things to erase information from the universe, thus challenging our understanding of the basic laws of nature. So that debate was vigorous and went on for decade after decade after decade. The reason it's interesting is because there's a very precise problem posed. So it's not some kind of thing like trying to understand a singularity or understand the Big Bang, or where you can just say, well, we're miles away from understanding. The challenges were posed in a region of space, the vicinity of the event horizon, where we thought we had control of the physics. And so that's really useful, because it means that it should be the case that calculations can be performed to resolve. The reason this challenge, this apparent contradiction, this fundamental problem, garnered so much attention is because it occurred, the problem came from physics that everybody thought they understood. So calculating in a region of space under conditions in the universe where we thought and assumed that we had full control of the mathematics and the theories. That's really interesting, because it sort of means you have a chance catching a glimpse of some kind of deeper theory by resolving this contradiction. So that's why more and more people got interested in the black hole information paradox.